Okay, so today we're going to continue our discussion on the 4 modes of convergence of a random variable sequence to a random variable limit. So last time we talked about 4 modes of convergence, and I'm going to recap their definition. And we'll give you some examples. So the first one is what we call convergence in law. And we write this, xn converge in law to x. So how do we define this? It's defined based on the convergence of the CDF function. So that is, we have the CDF function of xn at a particular value x converge to the CDF of the limit x at the same value. So it's a pointwise function convergence. And as n goes to infinity for sure. And we want to have it for all the x where the limit CDF fx is continuous at, where this is the continuous. Okay, that's the first definition. And we said that for this convergence in law, there's no requirement on the joint distribution of x and x. And the second one is what we call convergence in probability. And we write this. Okay, and the definition for this is that for any positive neighborhood size, we have the probability that the xn is not in that neighborhood of x, which means that their distance is greater than epsilon. And we want this probability to converge to 0 as n goes to infinity. So as we said last time, this will require the joint distribution of xn and x. The third convergence is called the convergence in the rth main, and we write xn converge in rth mean to x. Okay, and for this one, it's actually about the expectation. So we want the expectation of the absolute difference raised to the power r converge to 0 as n goes to infinity. That's the third mode. And the fourth mode is what we call convergence almost surely, the strongest type of convergence. And what this requires is the probability that my xn converges to x. This thing holds with probability 1. So that's why this is also called convergence with probability 1. We introduced those 4 types of convergence. So except the first type, all the latter 3 types require joint distribution of xn and x. And I'm going to write it here. So these 3 all regard joint distribution of xn and x. Okay, so we're going to give you some examples to demonstrate how each type of convergence means, each mode. And so for the first mode, right, convergence in law, the first one, the most famous examples, the most famous example is the central limit theorem. That's exactly regarding the convergence in distribution in law, right? So in the central limit theorem setting, what is each xm? So we can consider that here we have a set of sample, and that is IID. So we can say our sample, we can write it as y1, y2 to yn. And they are IID, independent, and they follow the same distribution. So here, this is something I want to make a very brief clarification. In classical statistics, we use a sample to refer to a set of observations. But later in machine learning, you might hear people talk about samples. And sometimes when you use the plural form, they are referring to each observation as a sample. So they say, we have n samples. But in statistics, that's not very conventional. We actually refer to all the n observations as one sample. So I think there's just some confusion about the usage. But what I want to say is that in your own writing, right, in your own report, your own dissertation, your thesis, you need to be consistent yourself. So just define what you mean by a sample in the very beginning. That's just my suggestion. Okay, so yeah, I'm going to use the statistic way. So given this IID sample, then we can define Xn, the notation we use here, as the average of my sample. I define as Yn bar, which is the average. Okay, and then what we are talking about this convergence is actually given a sample of size n, we compute its average, we call it Xn. Then as my sample size grow, I get more and more data points or observations, my sample size grow, so my corresponding Xn, the index n, will also grow. And then you see, here in the central limit theorem, I'm just talking about the distribution of this average, sample average, as n goes to infinity. And central limit theorem gives a very strong result. That is, no matter what the original distribution of your sample is, as your sample size goes to infinity, your average, sample average, will become normally distributed. That's very strong result about central limit theorem. And later we're going to give you an example. And you can also see that in my discussion so far, there's no requirement for this first mode of convergence. There's no requirement on the dependence of the xn's. So I'm not saying, okay, my xn plus 1 are independent or not. So in this first mode, we don't need that. We don't need that requirement. So for example, when we talk about the distribution of xn, we do not look at the distribution of xn plus 1 or xn minus 1. So we don't care about that. So in that case, when we have the sample size grow, it could be that we add new observations to this existing sample. If that's how we grow our sample size, then you can clearly see my xn and xn plus 1 will not be independent because they share n data points. On the other hand, they may be based on, so the n plus 1 sample may come from another independent draw. In that case, xn and xn plus 1 will be independent. But no matter what, here, this result, the convergence in distribution, has nothing to do with that dependence or independence of xn and xn plus 1. I'm just going to make a clarification here. And for all the examples, like about the convergence, right? All the 4 modes of convergence, you can try to interpret it, if it's better, to think about xn as a sample mean of sample size n. That if that can help you understand why we have a sequence of random variables. Okay, and also regarding the mode 1, I'm going to give you another example that's in our notes. So basically, here we just make things simple, okay? We just try to define the xn and x as point mass. So basically, what I'm going to do is that I will just define xn as 1 over n. It's a point mass constant, and x as 0. Okay, we are simplifying the thing. But you see, a constant can be considered as a special type of random variable where all the probability 1 is at a mass. Here, all the probability is at 1 over n. Here, all the probability is at 0. Then, what is the corresponding CDF? Let's go back to the definition. So in the corresponding CDF, it's very clear that fxn at a value x, we can actually write it using this notation. We're going to get familiar with that. Indicator function 1 over m to positive infinity x. So what does this mean? This means that it takes value 1 if x is greater or equal than 1 over m, and 0 otherwise. This is aligned with our definition of a CDF, right? Basically, before x reaches 1 over m, my probability, cumulative probability, stay at 0. Once x reaches 1 over n and beyond, my cumulative probability becomes 1. So that's just like a step function CDF. And this is also aligned with our discussion that when there is a positive point mass, we have a jump in the CDF. So here you see when we reach 1 over n, CDF jumps from 0 to 1. So similarly, you see, we have the CDF of the limit written as this. Okay? Then the question is, do I have that pointwise convergence of the CDF functions? That's our question. So you see how the functions will change. So if we draw a plot, right? So it's actually this x. Okay, we will have this f, x, and x. So if we draw a plot, let's say 1 over n is here. Then the CDF will look like, okay, it's 0, 0 all here. And then suddenly, so this is circle, suddenly I will jump to 1 and then 1 afterwards. That's the form of my CDF. And how will it change as n grows? You can see as n grows, 1 over n will diminish, right, towards 0. So this point will move towards 0. So it'll move in this direction. But if you have taken an analysis class, you will know that 1 over n will get close to 0, but never reach 0. So that's why this point will getting closer and closer, but it will never reach 0 exactly. And how about my limit CDF? My limit CDF, I'll draw it here. My limit CDF, this is 0, fx. My limit CDF will have the solid point exactly here, right? So that's my limit CDF, and its circle is right here. So therefore, we see that we can intuitively see for all the values except 0. So for all the values here to the negative on the negative x or any positive x, my fxnx will converge to fxx for sure. So what I'm saying is that for any x that is not 0, I can have my fxnx converge to fxx. So I have that. How about 0? 0 is a tricky point. So for me, for 0, right? So for 0, okay, for x equals 0 here, I have fxn 0, this point here, always taking the value 0. Because as I said, this solid point will never reach 0. Right? 0 will never be in this domain. 0 will never belong here, no matter how large the n is. But at the limit, fx0 is 1. So we will not have the convergence here. But this is not a real concern for us because 0 is not a continuity point of the limit CDF. So the limit CDF here is discontinuous. So that's why 0 is not in our consideration. And that's why you see in our definition of the convergence in law, we make an exception for those discontinuity points. Okay, so here 0 is just outside of this set, continuous set. So that's why here 0 is a discontinuity point, so we don't care about it. And for the other points, we do have convergence. So we conclude that we have xn converge in law to x in this special case. And even though we're using the real series and a real sequence and the real limit as example, but still it demonstrates the point. The real number is just a special case of a random variable. Okay, that's the case. Okay, another example, example 2, I'm going to give you is to show, okay, this is something we said already, but just as a good reminder. The second example we are going to say is that the first type of mode doesn't imply the second type of mode. So in other words, what I mean is that convergence in law does not imply convergence in probability. So for this counterexample, the easy one to think of is independence. Okay, so for example, let's look at this. My xn is a random variable, follows normal distribution with mean 1 over n, variance 1. And my limit also follows normal distribution with mean 0 and variance 1. And I have these two things independent. So in probability, we often use the sign orthogonality to mean independence. Okay, so when that happens, then you can see that we have this xn converge in law to x. This is very obvious. You can still prove it using the definition of convergence in law. Just write down the CDF here and show that they converge. Here, there's a little tricky thing I want to say technically, because the normal CDF does not really have a closed form. You cannot really write it out, but you can write out the density function in closed form. And the CDF is just an integration of the density, right? So if you can show that here, there's something a little technical because we want to show, okay, here, the convergence in the density will imply the convergence in the CDF. That's something we need. And then you can do that. Okay, so but still, this is something we can show. But given the independence, we will not have xn converge in probability to x. This is something I talked last time, right? The reason it's not is because the convergence and probability require the xn and x behave similarly. If we think about the realizations I talked about last time, in every realization, I must have the xn and x be very close to each other, right? And independence will not guarantee that. So that's why we will not have convergence in probability here. Okay, and another thing I want to say is that this is something very interesting. So this is an example I'm going to make sure you pay attention. So this is an example where we can say that, so basically we can have convergence in we can have convergence in probability, and we can also have convergence in arithmean, but neither of them would imply convergence almost surely. So here I'm saying that the second mode doesn't imply the fourth mode. And the third mode also doesn't imply the fourth mode. So to be exact, what I mean is that convergence in probability does not imply convergence almost surely. Convergence in the arithmean doesn't imply convergence almost surely. So convergence almost surely is the strongest requirement, as you can see from our last discussion. It requires every realization, basically, that sequence, that real number sequence need to converge to that real limit. And we want to have that hold for all the realizations. So in this case, this is a very famous counterexample. And if you understand it, you'll think it makes a lot of sense. Okay, so basically this counterexample is created to specifically violate that almost sure convergence. But still, with the violation of that, we can have this setup to satisfy convergence in probability and convergence in Rth mean. So let's see how we do the creation. So this is a counter example. Okay, and what we're going to do is that we are going to first use a uniform random variable to start the creation. This is a very common technique in probability. So, you know, all the random variable distributions can be created from a uniform distribution. And here, we're using that idea to do the construction. Okay, so we first draw a random variable uniformly from 0 to 1. Okay, and then how do we create a sequence? Our sequence is created as follows. So when we talk about x1, okay, we just let it, basically, we consider the whole interval 0 to 1. So whenever z falls into it, we give x1 a 1 value. So in other words, we get x1 an indicator of this function. Okay, let me write it. 0 to 1 z. This is how we define it. In other words, as long as z falls into this interval, I give my x1 value 1. Otherwise, I give my x1 value 0. So you see, by the definition of z, then x1 will always take value 1. So it's actually a constant 1. And then I do my construction as follows. So for my x2 and x3, what I will do is that I will split the interval 0 to 1 into 2 halves. I'll scroll this up. Into 2 halves. So whenever z falls here, I give my x2 1. Okay. 0 to 1 half. This is my x2. And my x3 is for the second half of the interval. Okay, that's my x3. So you see, these two things cannot be both equal to 1. That's the construction. So whenever x2 takes value 1, it means that z is in the first interval, so x3 must be 0. Or if z falls into the second interval, x3 is 1, x2 must be 0. So they are, only one of them could be 1. That's the trick of the construction. Okay, then you see how I continue. In the next step, I'm going to further divide the interval into halves. So basically, I'm going to do a separation here, here. So 1/4, 3/4. So I get 4 intervals. So this will give me x4 for the first interval, x5 for the second interval, x6 for the third interval, and x7 for the fourth interval. So again, you see, for those 4, out of those 4 random variables, only one of them can take value 1, and the other must be 0. So because they are exclusive again. So you see, I'm just continue doing this to grow my sequence. That's how my sequence will happen. So you see, how will the sequence look like? basically, let me give you a summary. So you can imagine x1 will stay as 1 for sure, right? And I have x2, x3. They are a pair. x4, x5, x6, x7. Let me write this up. These 4 things are a group. So this is a group of 2, group of 4, and I can have a group of 8 and a group of 16 and so on. Okay, but what's special about the sequence is that only one of them can be 1. Okay, so their sum is 1, and the sum of these 4 is 1. The sum of these 8 is 1, and the sum of these 16 is 1. So you see, no matter how far I go into my sequence, I will still have a group, a larger and larger group, right? I will run into a group, and within that group, there must be one of them is 1, and the others must be 0. So you see, think about our definition of almost sure convergence. Does the sequence converge almost surely? Think about the realization. So if I just realize the sequence for once, how will it look like? So Zach, you are shaking your head. You don't think it converges, right?
Yeah, because in the limit, the variable that it would converge to, I think, would be a variable that's just 0 always. But in the sequence, you'll always have 1 at every set of 2 to the n that's equal to 1.
Exactly. So even though 1 appears less and less frequently as you get into the sequence, but still there will always be some 1 popping up. So that's why it will violate the convergence, right? So by this setup, the sequence for sure doesn't converge almost surely. It doesn't converge to anything. And so that's why it doesn't converge to 0 almost surely. But if we think about the convergence in probability, then it's a little different. Okay, convergence in probability, it means that fix an n, okay? We fix an n and we look at, so if we think about the limit as 0, let me write it here. 0 is our limit. We fix an x and n and we look at all the possible xn and what proportion of those xn is far away from 0 by distance epsilon. So think about it. So given epsilon, and we think about what is the probability that this one, I'm writing here, xn minus 0 is greater than epsilon. Here, because my xn are non-negative, right? And 0 is 0. So I can simplify this by just have probability xn greater than epsilon. So these two things in the special case are equal. Then you see, what is this probability? So that means you can consider my realization again. Think about that image, right? Out of all the possible realizations of xn, what is the probability that this xn is greater than epsilon, which means that it's not 0? Then you see that one, this probability is getting smaller and smaller because we will be less and less frequently to run into a 1, right? Here, xn can only take 2 values, 0 or 1. So to be greater than epsilon, it must be 1. And therefore, you see, I can write this as xn equals 1. It's that. So therefore, you see that I basically know this probability is shrinking down to 0. So that's why I'm good. And for the derivation, I'm going to simplify that calculation, but you can just do the calculation yourself. Basically, this probability would depend on the position of n, right? So you will need to see where n is in this long sequence. And then for that particular group, you can calculate the probability of being 1. So like here, in this group, the probability of being 1 is 1/2. This is 1/4. This is 1/8. This is 1/16, right? And it goes down and down and down. And so you know that. So we have convergence in probability. So therefore, you see, Convergence and probability is a much looser definition than almost sure convergence because it says nothing about a particular realization. It's just about the cross-realization overall behavior, right? So that's why we can still achieve that here, but not here. Okay, how about convergence in Rth mean? Let's also think about that. Okay, this one. It's similar to convergence in probability because it's about an overall behavior. So here, this is the definition of the convergence in Rth mean. Again, because here we have x0 taking only values 0 or 1. So you see when it's 0 or 1, the absolute value can go away and the Rth power can go away because 0's Rth power is 0, 1's Rth power is 1, right? So this is basically equal to this, okay? And then you see, what is the expectation? Because this is 0 or 1, right? X is 0, 1. This is something you want to know. It's a very useful trick. For a binary random variable, its expectation is just the probability that it takes value 1. So still, this goes down to 0. So you see, in this very interesting construction, we can actually achieve convergence in probability, convergence in Rth mean, but not convergence almost surely. Okay. Right, do we have any questions about this example? Okay, we're good. Okay, so one more thing is that it's not just this way around. The other way around doesn't work either. So basically, although I said convergence almost surely is very, very strong, still it's not the, I would say, it does not imply convergence in the Rth mean. So from 3, we cannot go to 4, but from 4, we cannot go to 3 either. And here we're going to give you another interesting construction. So what I'm saying here is that convergence almost surely does not imply convergence in the Rth mean. Why is that? Think about it. Why doesn't convergence almost surely not implying convergence in the Rth mean? So here, if we want to construct a counterexample, we need to think about the definition of the convergence in Rth mean, which is regarding this expectation. Okay, so what this actually says is that, so for this convergence in Rth mean, the value of the xn, okay, this value will actually matter. So basically, when we try to construct a counterexample, you need to think about the case. That is, even though I can have my every realization converge, right, to the limit. That's the definition of almost sure convergence. But still, I may have somewhere in the sequence that makes the value of xn very, very large. So that one particular violation in one realization may actually violate this convergence in the expectation. That's something we're going to construct, okay? So still, we're going to utilize this uniform random variable for construction. We let z still be uniform 0 to 1. Okay. So here, this is an open interval 0 to 1. And we define xn, the random variable sequence, to be this, to be a large constant 2 to the power m with a constraint on the interval 0 to 1 over m, z. So what does this mean? This means that if z falls into this shrinking interval, then my xn will take a large constant 2 to the n. Otherwise, xn will take value 0. So you see, as my n grows, this interval is shrinking, right? 1 over n is getting closer and closer to 0. So it will be more and more, it will become less and less frequent for my xn to get value 2 over n. And it will be 0 otherwise. So you see, the frequency for xn to be non-zero is decreasing as n goes to infinity. But it's still somewhere in the sequence, it will reach the value 2 to the n. So how do we think about it? Still, I think it's the most straightforward way to think about realization. So let's think about it, right? So what happens if my first realization, let's say I call it Z1. The first realization is 1/2, okay? 1/2 can be drawn from this uniform interval. Then what will happen about the realization of x1? So think about the first realization. What will be my x1? In the definition, 0 to 1, right? Z is in it, so it will take value 2. That's my realization. How about my second x2's realization? Okay, 0 to open 1/2, so Z doesn't fall into it, it becomes 0. And so on. All the subsequent realizations will be 0, 0, 0. So you see, the limit of the sequence is indeed 0. We don't have an issue here. How about my other realization? Let me just give you a second realization. Let me make it a little smaller. So for example, let me put it 1 over 32. So then you see in this realization, this will be 2, right? The first one, the interval 0 to 1/2 contains it. The second one, 0 to 1/4 contains it. So that will give me 2 to the power 2. That's 4. And x3, sorry, this is a typo. Yeah, 0 to 1 over 8 still contains it, right? That will give me 8. And x4, 16. And then x5, that will give me 0. And then 0, 0, right? Everything after the 0 will become 0. So still, I'm converging to 0. So you see the trend of this sequence. Basically, why we have almost sure convergence is because for this whole sequence, right? As long as one of the value reaches 0, all the subsequent values will stay at 0. So we have convergence in every realization, and that's why we have almost sure convergence. However, this is not the definition of convergence in the Rth mean. For the convergence in the Rth mean, I'm going to write here. For the convergence in the Rth mean, what we need is that for a fixed n, we're looking at this. Suppose the limit is 0. We look at this. And again, here the xn's are non-negative, so we can take away the absolute sign. So it becomes this in this special case. And then you see, no matter how, so basically, even though in some realization, okay, for this particular n, let's think about n equal to 3, okay? So even though when n equal to 3, many of the realizations will have the x3 equal to 0, but some realization may have x3 equal to 8, right? So that's just because whenever z falls into that interval, so when z is in the interval 0 to 1 over 3, then we will actually have this x3 takes value 8. So that's why we will, for fixed n, we will always have some realizations of xn that take a very large value, even though most of the realizations will be 0. So that large value will counteract the small probability for xn being non-zero. And so we can see that what's the probability of this xn being non-zero? Right, so this one we know by the definition of expectation. It's actually equal to 2 to the n times the probability xn is greater than 0. That's it. And then xn greater than 0 is equal to the probability that z is less than 1 over n. Okay? Oh, sorry, I forgot this. My bad. R. Okay? R power should stay here. Because z is uniform between 0 and 1. So you see, we get 2 to the power nr over n. That's it. So basically what I'm saying is that even though the probability of z less than 1 over n is decreasing as n grows, but this decrease is not large enough to counteract the increase in the value of xn. So you see, this thing actually goes to infinity as n goes to infinity. It doesn't go down to 0. So that's why we have this thing doesn't converge in the rth mean to 0. Doesn't. We have that. Right, so we give you a specific example. So you see the difference in the convergence almost surely and convergence in the rth mean. So basically for convergence in rth mean, it's not enough for us to just have every realization of the sequence converge to a limit. That's not enough. We still need to look at the values of a particular n and see how the average of the realizations, which is our expectation, look like. Here, the average is actually this. So it's actually exploding. It's not converging. Okay, that's all. So that's all I want to say about the counterexamples to summarize. So we said that convergence in law cannot imply any of the later three. So convergence in law is just by itself. It's the weakest convergence. And convergence in probability or convergence in the rth mean, neither of them can imply convergence almost surely. And finally, convergence almost surely will not imply convergence in the rth mean either. So basically, I'm going to give you a diagram to actually give you the relationship between those four things. Okay, so probably I think I'm going to, let me see, whether a linear diagram will be good. Yeah, okay, so 1, 2, 3, and 4. So shortly, I'm going to give you some positive relationship. Now we're just saying you cannot do this, you cannot do that. But later we'll talk about some positive things. Okay, so maybe I can put this notation here in case you forgot which one corresponds to which. Okay, so these four modes. So what we have said is that, okay, this one cannot imply this one. And this one cannot imply this one. This one cannot imply this one. And neither this direction. So we have said those. So those four relationships won't go through. So then what can go through then? So, okay, so that's what we said in the notes. So I'm going to skip part of the notes. I'm going to come back to the monotone convergence theorem and Lebesgue's dominant convergence theorem. So those two important results, I want to give you some introduction. But now let's first talk about what we can say. The first thing we can say is this. I'm going to use a red pen. So the first thing that actually indeed hold is this 4 implies 2. Okay? Almost sure convergence does imply convergence in probability. That's one thing. Another nice thing is that convergence in the rth mean implies convergence in probability. So this direction also goes through. Finally, convergence in probability implies convergence in law. Okay, these positive results are very useful because, you know, as I said, in statistics, we mostly want the first two modes. We want to have either convergence in distribution. That's what we need for asymptotic distribution, right? So when we talk about, let me give you some example. So when we talk about this convergence in law, we almost use or mostly use it to derive the asymptotic distribution of a statistic. And that's why everyone is here to learn this class. That's very useful. And this is because we want to have a very nice form of our statistics so we can do hypothesis testing very easily, right? When you have a statistic for doing a test, if you can derive its asymptotic distribution under the null hypothesis, then you can calculate p-value. That's very practical. Okay, and for the second thing, convergence in probability, we often use it to talk about the consistency of an estimator. So basically, we want to know if we have a large enough sample size, does my estimator converge in value or converge in probability to the true parameter value, the limit, right? That's my true parameter. And then that's something we desire for the estimator, right? So that's why this is very important for us. So in order to derive those two results, you see the red arrows give us some convenience. For example, it could be that it's easier to prove convergence almost surely. If you can do that more easily, you will naturally have convergence in probability, problem solved. Or if it's easier to prove convergence in the Rth mean, you can do it. Then it implies convergence in probability, problem also solved. So in statistics, convergence Rth mean is also interesting. As I said, it can imply the MSE, right? So I'm saying this. So when R equals 2, it's regarding the MSE going down to 0. That's also desirable. Okay, yeah. So from second to first, from convergence in probability to convergence in law, although I'm saying that this implies that, but still for the asymptotic distribution purpose, it's not done yet, because knowing a convergence in law to some distribution doesn't mean that you know what that distribution is. So often you still need to derive that distribution. Okay, so how do we prove it? Okay, so you see, this is something we're going to give you as very important result. So the first thing is, how do we prove 4 that can give you 3? In other words, how can we prove that almost sure convergence would imply convergence in probability? 4 gives you 2. I made it, sorry, 4, 2, not the 3. You cannot go to 3. Okay, how do we show this? In order to show this, we need to give you an alternative definition of almost sure convergence. So that will give us the background to do it. So this is a little abstract, but I hope I can make it intuitive. It's alternative definition of almost sure convergence. So before we talk about it, we need to actually give you something which is very important in, maybe I'll do that later. So the Borel-Cantelli Lemma. I think some of you might have learned this before from either a probability theory class or from a measure theory class. But this is something not intuitive, but actually very important. And it's kind of related to here. Okay, but let me finish this alternative definition first. So this alternative definition is that for any epsilon greater than 0, see, we're in a setting similar to the convergence in probability. For any fixed epsilon greater than 0, we would have this probability that is xk minus x less or equal than epsilon for all k greater or equal than n, I'll have this probability converge to 1 as n goes to infinity. Okay, so I'll give you maybe 30 seconds to think about this. How is this different from the definition of convergence in probability? And I can write down the convergence in probability definition to help you compare the two. So definition of convergence in probability, that is the probability xn minus x less or equal than epsilon converge to 1 as n goes to infinity. Okay, so directly look at and compare these two things. What's the difference? Again, you can think about realizations to help you visualize this whole thing.
Is this the same thing as like the strong versus like the weak law of probability? Because it seems like one implies that you can never go more than epsilon above and below once you get past like the nth observation, and the other implies that you can, but that you're just like overall staying like
Exactly. Yeah, exactly. Yeah, you made a good point. That's the essence. So yeah, again, so the first one, you see the key difference is that, right? So the key difference is that you're not talking about the nth xn, right? You're not talking about the nth value in the sequence. You're talking about all the numbers after it, right? So it's n plus 1, n plus 2, and so on. You require all of them to be in the neighborhood, absolute neighborhood of x. That's what you require for this one. But for this one, you're just talking about xn. So therefore, you see, this one is requiring that, okay, as n goes large, this probability is converging to 1. But you see, when you have a particular sequence, like one realization, it's still possible that xn is in the neighborhood, but xn plus 1 is not in the neighborhood. So that can still happen for this requirement. But for this, it cannot happen. You just require all the later subsequence to behave in a coherent way. So that's why it's much stronger. And if you think about the counter example we gave before, okay, let me put my paper back. If you think about this counter example, you will not satisfy that almost sure requirement, because you see, whenever, so even though here you have a 0, and that's in the absolute neighborhood of the limit 0, but still later you will encounter another 1. So that 1 will not be in the neighborhood. So that's why this sequence, this counter example, will not satisfy this. But as we have already seen, it can satisfy this, because this one is about the overall behavior, looking at all the realizations together. Okay, does that make sense? Okay, sounds good. And one more thing I want to say, why I say this is related is because probably I think it's a good time for me to start talking about that Borel-Cantelli Lemma that can help you understand. I think this example can help you understand it better. So that's an important result we want to introduce, right? But to be honest with you, I think this Borel-Cantelli Lemma, to me, when I first learned it, it was just a mathematical result. I didn't actually think too much into it. But now this is like I'm teaching this class, right? So I think the more I actually realize it using concrete examples, I think I understand it better. So let me try to talk about that as a side note, and then we'll come back to the main thing. So let me put this in the box. So I'm going to call this I'm going to talk about the Borel-Cantelli Lemma. Even though this is the probability result, it's not really specific to a random variable sequence. But you know, a random variable is directly equivalent to an event, right? So whenever that event happens, we can say, okay, my random variable takes value 1. So you see that the one-to-one correspondence between those two. And here, Borel-Cantelli Lemma is about measuring the event in terms of their probability. Okay, Borel-Cantelli Lemma has two statements, very interesting, and they're both important. So basically, here my setting is that I have a sequence of sets or a sequence of events. So A1, A2, AM, and so on. And you can actually think about what we have talked about before, like XN is the indicator whether AN occurs. So then that can make the event as a binary random variable. You can think about that way. So what this is talking about is this. So if I have the total, the sum of their probabilities, so I'm saying that for J going from 1 to infinity, if the probability AJ, the sum is finite, it's not infinity, then I would know that the probability my AJs occur, I would say, this is a very important note, very important phrase, infinitely often. This thing holds with probability 1. So we often write this infinitely often in short as I dot O dot. What does it mean? What does it mean? So intuitively, you can think about this way. So infinitely often, I'm going to switch back to my black pen. It means that, okay, I'm going to write it. I1, A2, maybe AN, this thing. So it means that no matter how late I cut into my sequence, there's always, okay, I got a question here. Let me see. Is it chat? Oh, okay, no problem. So A1, A2 to AM here. So no matter where I cut in the sequence, I always have infinite number of events after my cut here happens. Okay, infinite number of events occur. This is what we mean by infinite often. And it has nothing to do with where my cut is. I can cut it very, very late in the sequence, but still after my cut, there are still infinite number of events happen. That's what we call infinitely often. Okay, and how can we represent this, right? So can we actually write this term, AJ occurs infinitely often? Can we write this in a mathematical term used by set operations? Actually, we can. Okay, let me give you some idea. Maybe you can actually do this yourself. What does it mean that after, let's say, if I cut it at n, okay? Let's say what does it mean that there are infinite number of events occur including and after AN. So if I cut right before AN, then what does it mean that after this cut, I have infinite number of events occur? Can we represent this using a set operation? Or sorry, let me step back one step. Maybe I'll cross this out and I'll use a new paper. Probably I didn't make this clear. Okay, so what I actually mean is that maybe we do one thing at a step. So let's say, again, A1, A2, AN minus 1, AN plus 1. Okay, if I cut here. what do I mean? That there is at least one event that happens after this cut. So from let me start. At least one of am plus 1 occur. How do we represent this using set operation? By set operation, I mean union or intersection. Can you represent this?
By union, I guess.
You say union, right?
Yeah.
Yeah, correct. Yeah, definitely, that's right. So here we can just write this. J go from n to infinity, aj. I take this union, which means that if one of them takes value 1 or one of them occurs, then this union occurs, right? So that's why we can represent it this way. And infinitely often means that no matter how I move my cut down to the sequence, I can still have the union of the remaining sequence actually occur. That's infinitely often, right? No matter how late I move into, there must be some event afterwards, occur afterwards. So therefore, you see, infinitely often, it means that this means that no matter where I cut, no matter how large n is, this thing always occur. So no matter how large n is, at least one of am plus 1 and remaining must occur. That's the definition of infinite often. So in other words, for all the n I can think of, this event, this union must occur. That's infinite often. And then what set operation do I need to use? If we require that all the things hold together, should I use union or intersection?
Intersection?
Yes, correct. Intersection, right? So union means one of them occur. That's union. An intersection means all of them must occur. So therefore, you see, mathematically, this becomes, we take the intersection for n, go from 1 to infinity. For each n, we take the union for j going from n to infinity. That's it. Okay? So therefore, the probability that aj occurs infinitely often, the statement of the Borel-Cantelli Lemma is actually equivalent to the probability that the intersection of n and the union from n to infinity, this thing occurs with probability 1. That's it. So these two things are equal. That's the key point. And so realizing this expression is the key for us to prove the Borel-Cantelli Lemma. That's it. Okay, so basically, that's what I want to say. That's the Borel-Cantelli Lemma. And then you can see why this would actually hold. Okay, so coming back to the statement.
Hi, Jessica.
Yeah.
I look at the chat. Mingtao Xia also raised a point, and I also look at the Wikipedia. I think that probability should goes to 0. Infinitely many of them.
Yeah, exactly. My bad. So sorry, that's a typo. Yeah, that's 0. Sorry, that's a very, very important correction. Yeah, correct. Thanks for letting me know. Yeah. Exactly, that was a typo. Yeah, I mean it's 0. And intuitively, you can see why this is true. Because you see, here is the summation of the probability, right? Whenever this is finite, it means that some of the probabilities must be very, very small because you have infinite number of things to add up to the sum. right? So some of the probability, some of the events must have very, very small probability. So intuitively, you would expect, okay, maybe not all of them will happen infinitely often. That's just the intuition. But how do we actually prove it? And that's here. Here it is. Now with this expression, it becomes, okay, yeah, I need to correct this as well. But here, no matter it's 0 or 1, this always hold, okay? This is the relationship always hold. We're just going to prove why this is 0. And how do we do it? Here, we're just going to utilize this definition. Okay, so to prove this first statement, all right, we want to write out the probability aj infinitely often. We know it's equal to this, right? And because we know the probability of an intersection is always less or equal than the probability of each set in the intersection, or we used to take the intersection for. So therefore, we can just make this less or equal than the probability of this thing, j from n to infinity aj. And this actually holds for any n, because we just get rid of this intersection, and that's it. And then we're going to do a very famous but simple way of finding an upper bound on a union and the probability of a union, right? The upper bound is just the summation of the probability of individual sets. And this we can do as summation j from n to infinity probability aj. And we're done. Okay, why? Because we know that since the summation j from 1 to infinity p aj, this is finite. Because of this, we know that after we reach n, right? So we take the n to infinity, it's just a partial sum. Because this total sum is finite, so the partial sum must go down to 0. Since this, we have the partial sum this thing must go down to 0. Otherwise, this will not occur. So these two things are equivalent. So basically with this, then we can have this thing go down to 0. And we're done. Okay, so that just proves the first statement of Borel-Cantelli Lemma. So in other words, if we have a finite sum of a sequence, then we know that as we get later into the partial sum, it must go down to 0. That's the requirement for the convergence of the series. And then this thing is actually giving us an upper bound on this infinite often event. And because this is lower bound by, you see, this is lower bound by 0. And if this is going down to 0, then we know this thing must be 0. That's it. Okay, that's the first part of Borel-Cantelli Lemma. The second part is actually what we use even more often. It's regarding this. So it actually can be considered as a partial converse of the first statement. So you may wonder, okay, so coming back here, you may wonder if this is finite, then this is 0. What if this is infinity? Then what will happen to this? And the second statement is about that. It's about when this is infinity, what happens here? Okay, so for the second statement, if okay, we have this. And we need to add an additional condition. And AJs are independent. So when both happens, then the probability AJ occurs infinitely often is 1. Okay, so basically we're saying that if we have independent events and the sum of their probabilities is infinity, then we must have these events happen infinitely often. In other words, infinite number of events occur. Okay, then how do we show this? And so the proof of this part is a little bit trickier. So basically we need to still utilize this definition of infinitely often. This is still the key. But in order to make use of the independence, we need to change. So we need to actually play with the complement of the sets. So basically the trick here is that if we have independent sets, then the probability of their intersection is equal to the sum, is equal to the product of their probabilities. That's because of the independence. Okay, but before we talk about that, I want to give you a very important intuition about why we need this independence. So we can think about we can think about the realization of the Borel-Cantelli Lemma as coin tossing. Okay, so example of this is coin tossing. You can think about my AJ defined as the event that the jth toss is 1 or is a head. So, and I keep on tossing. In the case of coin tossing, we assume that tosses are independent of each other, right? And then you see what this means is that if my probability of coin tossing sum up to infinity. So for example, if each toss has probability 1/2 to be a head, then this will definitely be infinity, right? And then I can imagine that in my continuous coin tossing, infinite number of my tosses will be head. So that's expected. And why do we need independence? What if we don't have independence? Then what will happen? So if we think about the violation of independence, the easy way is to use totally dependence. Total dependence, which means that I basically just toss my coin for once. So I toss it for once, and the subsequent tosses are just copies of my current toss. So they're totally dependent. When that happens, you see, even if my head, okay, so if x1 is a coin tossing, so maybe I can just say A1 is tossed with 1/2 probability. And if I just copy A1, so that A2, A3, and so on, they all equal to A1. So if I get a head, I will always get a head. If I get a tail, I will always get a tail. So in that case, you can see the probability of AJ occur infinitely often is what? So here you see my PA1 is 1/2, PA2, 2, PA3. These things are all equal to 1/2. So you see the first condition, this is infinity. We still have that. However, in this case, when they're totally dependent, the probability AJ happens infinitely often. It's just 1/2. It depends on whether my first toss is tail or head. When it's head, it's all head, so infinitely often. When it's tail, they're all tail, so there's no event that is a head, right? So then I I just don't have it infinite often. So it's either infinitely often or not. And that totally depends on my first toss. And to clarify here, I mean infinitely, but by happening, I mean the toss is a head, okay? So when it's a tail, it doesn't occur. So, or changing this, yeah, to make it head is a head. So that's why you see this statement doesn't hold in this case because here I have total dependence. I'm just trying to explain why the independence assumption here is very important. We cannot get rid of it. Okay, so I think I'll stop here and we'll come back to that. So the Borel-Cantelli lemma is kind of like a deviation from our main discussion, but as it's related to the almost sure convergence, so I'm introducing it here. So next time we'll come back, we will continue about our alternative definition of almost sure convergence, and then we can directly see why almost sure convergence implies convergence in probability. Okay, so we will assign the first homework today, and that will be due in 2 weeks. So you will need to submit your homework by scanning your writing, or if you use LaTeX to type, you should just upload your PDF to CCLE for submission. Okay, so I'll see you on next Tuesday. Bye.
Thank you.
Thank you.